All right. Hey, everybody. We are back with another exciting guest speaker session. For people who have joined us from outside Cohere community, feel free to check out our channel at ML Healthcare in the Discord channel for the Cohere AI community. Today we have Hallee with us. Hallee is a PhD candidate at CS SAIL at MIT, advised by Dr. John Kotak and Katrina Dalka. Her research focuses on developing interactive and human-centered AI system for medical imaging analysis. She's going to talk about efficient segmentation of new biomedical imaging datasets from scratch. That's an important problem in today's world, and she's going to cover from basics to the advanced. Thank you, Hallee, for taking out time and speaking at today's sessions. We're super excited to hear about that.
Yeah, thank you so much for inviting me. So I'm excited to talk to you today about efficient segmentation of new biomedical imaging data sets from scratch. So image segmentation is a core part of biomedical image analysis. So specifically this process of analyzing an image and outlining different regions of interest. Here I have a bunch of examples of some of the different common modalities in medical imaging and regions that people might be interested in segmenting. There's tons of different applications for segmentation in medical imaging, for example, in clinical workflows like radiotherapy planning and surgery. And just about any research that involves imaging will often involve segmentation as a first or an important step in the image analysis pipeline. More specifically, medical researchers are often defining new segmentation tasks. This is because they are either collecting new images, perhaps developing new image acquisition methods and modalities, or defining new regions of interest. And so many research projects begin with manual segmentation. Unfortunately, this process of manually segmenting images, basically annotating by hand the boundaries of all these regions, is really tedious and time-consuming. And this is particularly true for biomedical images, where it requires expert annotators to do the labeling. And users, like these researchers, often want to segment not just a few images, but maybe tens or hundreds or thousands of similar images in a consistent way. We can train deep learning models to automate some segmentation tasks, but that still requires upfront manual annotation to create that training data. So if we want to segment a new data set, a standard approach might be to first annotate some images and create a small training set, and then use that to fine-tune or train a deep learning model, and then continue using that task-specific model to segment the rest of the data. But this approach requires computational resources and machine learning expertise that's often not available to biomedical researchers. So with MultiverSeg, we introduce a new framework and system that enables users to efficiently segment new biomedical imaging data sets from scratch. This means without any previously labeled data. To use the system, users begin by specifying a few examples through interaction. The model then adapts based on those examples, learning from experience, but without any retraining. And then as the user segments more images, the system gets better at the user's specific task. So that with enough examples, the model can then be used to segment the rest of the images automatically. To go into more detail about how we achieve this technically, MultiverSeg is a system that takes as input an image that you want to segment, and then also user interactions like clicks or bounding boxes or scribbles. It can also be used iteratively, so the previous prediction is also an input. What's new is that MultiverSeg also has an input for a context set. So this set has example images and segmentation masks demonstrating the segmentation task that the user wants to perform. And so MultiverSeg can predict the segmentation of this new image conditioned on both these user interactions and also a set of example images and segmentation masks. So when applying MultiverSeg, there would be three phases to segmenting a new data set. The first part is interactive segmentation, where we don't have any previously labeled data, so the user just provides interactions to label that first image. But as we start to annotate some images and collect these examples, we move into interactive in-context segmentation, where the model is making predictions based on both interactions and context set inputs. Then the final phase of dataset annotation would be in-context segmentation, where the model is only receiving context set inputs and the user doesn't provide any interactions. And so we can segment images automatically. To put this more concretely, we can consider segmenting this dataset of brain MRIs. Perhaps I want to segment the gray matter in all of these images. You would start by taking the first image, providing interactions, and getting a prediction. But this prediction, it's not getting the whole region. So the user might also need to provide corrections and iterate with the model. But once they're satisfied with the segmentation, it would then be added to the context set that the system is conditioned on. So for the next image in the data set that you're segmenting, the model also gets information from the context set, and the user doesn't have to provide quite as many interactions to get an accurate segmentation. As more images are segmented and the context set is populated, the model becomes better and better at this specific task. And with a large enough context set, we can perhaps even segment the rest of the images fully automatically without any user interaction. Here's one of the results from our paper where we simulated segmenting many different segmentation tasks and data sets. The top two lines at the top are static interactive segmentation models. So for those models, you always have to do the same amount of work for every image in the data set. And with MultiverSeg, instead, as you segment more images, so we go sequentially through the data set, the amount of work to achieve the same level of accuracy declines. So it becomes faster and faster to segment new images. So in this talk, I'm going to cover two different works building up this system. First, I'm going to talk about a previous paper, ScribblePrompt, where we focus on improving this interactive segmentation step. And then in the later half of the talk, I'll talk about our more recent paper, MultiverSeg, where we introduced this whole system and created a model that addresses the second two phases. So within interactive segmentation, there's a lot of challenges, and some of them are specific to medical imaging. The first is that we want this entire system to be very user-friendly, and often different tasks, it's easier to use different types of interactions. For example, if you're segmenting a large area, it may be easier to just use a scribble or a bounding box, but if you're segmenting something thin like veins, clicks are easier to use, and users often have different preferences. We also want the system to generalize to new segmentation tasks, not only new types of images, but also new segmentation regions. We don't want our models to overfit. And lastly, we want to minimize latency because our users may not have access to powerful GPUs to run this model. We ideally want it to be usable on a laptop. There's been a lot of recent work over the past few years in interactive segmentation. In particular, you may have heard of the segment anything model from Meta, which is really excellent on natural images. Unfortunately, it doesn't perform as well on many biomedical imaging tasks, especially ones with more subtle boundaries, like the one on the right side of the slide here. Additionally, it uses really powerful vision transformers that are not very computationally efficient. There's also been a lot of works fine-tuning and adapting SAM for medical images, but they often focus on the single prompt or single interaction type scenario, and they don't generalize very well to unseen tasks or new scenarios. You might ask, what makes biomedical imaging different? I think there's a lot of unique challenges in interactive segmentation of biomedical imaging. For example, the subtle boundaries that I mentioned before, But also in terms of data that's available for training and model development, many public medical imaging data sets are small and quite specialized. And there's very diverse image acquisition methods that affects the distribution of images available. So in this previous work, ScribblePrompt, which was published at ECCV in 2024, we introduce a new system for interactive segmentation that works with multiple types of interactions, clicks, bounding boxes, and scribbles. It's very responsive to user feedback. It generalizes to unseen data sets and labels, and it also uses a lightweight CNN, so inference is fast, less than 1/3 of a second on a single CPU. I'm going to give a brief overview of kind of the interesting parts of training ScribblePrompt and some key results so that we can focus more of the talk on MultiverSeg. So like most interesting models, the training strategy is really key. And I think this is particularly important for interactive models where we want humans to use them and interact with them. We need to think about designing our training strategy to help these models learn to behave in a way that will be user-friendly. So with ScribblePrompt and other interactive segmentation methods, at inference time, the user would provide the interactions, but during training, we don't have access to this user. So instead, we used algorithms to simulate these different types of interactions. And a key part of the work was coming up with new algorithms for simulating realistic scribbles. There were two main parts to our overall training strategy. The first was simulating diverse interactions, which we did through different algorithms for simulating bounding boxes, scribbles, and clicks, and would also mix them during training. And then the second part was training on diverse segmentation tasks, which we did by building a really large collection of training data sets. This is something we've been working on over the course of several years and projects within our lab. And then very importantly, we further augmented our data with synthetic labels. I think the synthetic label strategy is a particularly interesting part of the work. In medical imaging, often there are small data sets where only one thing is labeled. So maybe there's a bunch of retinal images of the eye, and they always label the veins. If we train our model on just that data set, it's very easy for these models to memorize every time I see a retinal image, predict the veins. But that's not the behavior that we want for our downstream users. So during training, we also introduced synthetic labels to basically force the model to pay attention to the user interactions as opposed to memorizing certain segmentation labels for certain types of images. So we would generate synthetic labels by taking an image, running a superpixel algorithm, which clusters pixels with similar values, and then we would consider each of these superpixels as a possible synthetic label, and we would sample random labels during training. We found that equal mix of real and synthetic labels actually led to the best performance in ScribblePrompt. And I think this was really key to making the model responsive to user feedback, since I think a common failure case I've seen in SAM and some other models is sometimes for things it recognizes as objects, it's great at segmenting it very quickly, but if you try to segment something that's kind of out of training distribution, sometimes it will ignore your interactions. Here's some example predictions from our final system. So this first line is just prompting with scribbles, and ScribblePrompt produces a much more accurate, higher dice segmentation than these baseline methods. We have SAM as well as some medical variants and also some older interactive segmentation work. We also see that it performs well in scenarios where we simulate iterative interactions. In the middle, we're simulating 5 clicks, and in the bottom, we're simulating a couple rounds of scribbling. In this work, we did a lot of evaluations. We collected a data set of manual scribbles. We also did experiments simulating interactions, and we did a user study as well. For the sake of time, I'm just going to highlight the results of the user study. So in this user study, we compared ScribblePrompt to SAM. SAM was actually the strongest baseline in our experiments with the manual and simulated interactions. This was in terms of generalization performance. We had expert annotators perform segmentation tasks from our evaluation data sets, and they produced not only more accurate segmentations, but also spent less time per image using ScribblePrompt. And all of our participants in the user study reported that it was easier to achieve the desired segmentation when using ScribblePrompt. So in summary, ScribblePrompt enables users to segment new regions of individual images. And I think a theme throughout this talk is that success relies on a set of careful design decisions focused on ease of use and practicality. So now we have a system that covers the first phase of this dataset segmentation process. MultiverSeg, the framework, captures this, this entire process, but we still need models that can handle these other two scenarios. So now I'm going to talk about how we train that system. So similar to ScribblePrompt, to train the MultiverSeg network, we simulate interactive segmentation in multiple rounds of the iterative process. We use the same interaction simulator to generate the scribbles, bounding boxes, and clicks during training, but MultiverSeg has this additional input of the context set. During training, we sample variable size context sets up to 64, and that max size was just based on what we could fit on our GPU. When the model is deployed, we won't have the interaction simulator, and the user would provide the interactions. So the MultiverSeg architecture has a U-Net-like structure, and it takes as input this information about the target image that we're currently trying to segment, and also the context set, which contains previously segmented images. In this U-Net-like structure, we have a cross block, which shares information between the target image inputs and the context set inputs. And we do this sharing at multiple depths throughout the network, so at different image scales. Inside the cross block, we have the mechanism that shares information between the target features and the context features. So the first step is that we concatenate the target features with each of the entries in the context, the set of context features, and then we perform a convolutions on each pair. Then we average across the context set and concatenate the result with the target features and perform another convolution to produce our updated target features. We also perform another convolution on each of the context set features to get updated context set features. As with ScribblePrompt, we also use a large collection of biomedical imaging datasets for training and evaluation. We partitioned our datasets into training datasets, which are seen by the model during training, and then evaluation datasets, which we use in our results. Within the evaluation datasets, there were 9 validation datasets, which were split into validation and test data. The validation data from the validation datasets was used for things like hyperparameter tuning and model selection, because we wanted to make all of our model development decisions to optimize for performance on datasets not seen during training. But then in our final evaluations, we use unseen data from the test split of these validation data sets, as well as test data from these test data sets that were completely held out from the entire research process. Building off of our work with semi-synthetic labels in ScribblePrompt, we also use semi-synthetic data for training MultiverSeg. So in ScribblePrompt, we introduced this method for generating a single synthetic label from an image. But the challenge in MultiverSeg is that we need sets of images with consistent labels. And if you applied this process to a bunch of chest CTs, there's no guarantee that you would get superpixels with semantic consistency. So to address this, we would take the image and synthetic label and duplicate it and augment aggressively many times. So this way we would get a set of semi-synthetic images and synthetic labels that have some semantic consistency across them. Okay, so the last part is now, how do we have this entire MultiverSeg system, let's evaluate it. I first want to show some qualitative examples that I think help illustrate the advantage of this approach. So the top row here is ScribblePrompt. All of these models we prompted with the same single click, and they also have a context set of 10 examples available. So ScribblePrompt is only able to get one component of the target segmentation in this CT because it just has one click. This is the aorta we're trying to segment. In this slice, it has two parts because it's curving kind of around and going into the heart. And then the second row here, we also explored what would happen if you try to combine two off-the-shelf foundation models. So our ScribblePrompt model and MultiverSeg is another in-context segmentation model also developed by our group. So for example, we use MultiverSeg to segment based on those 10 context examples, and then we use ScribblePrompt to correct it with that one click. So this segmentation is better than just the interaction on its own, but MultiverSeg is able to segment this region even more accurately because it has learned to integrate information from the context set and the click simultaneously. And we see similar trends across a variety of different image modalities and segmentation tasks. All of these examples, as well as all the results I'm presenting here, are on our evaluation data sets that were unseen by the model during training. I think an interesting area of analysis with MultiverSeg is what's the relative value of different types of inputs. So here we explored the value of different context set sizes versus adding more interactions on the dice score of the segmentation, basically the quality of the segmentation. I think the main takeaway here is that doubling the context size from 1 to 2 has a much bigger effect versus going from 32 to 64 examples. So there are diminishing returns in scaling up the context size. And often to get a very high degree of accuracy, providing more user interactions is valuable. I think also another interesting question that we explored here is how do these interactive models compare to fully automatic models? To answer this, we trained several hundred fully automatic models on our evaluation data, so using all of the data that we had available, using NNUNet, which is a popular AutoML pipeline for medical image segmentation. And so you can see that very quickly, when you add more interactions, MultiverSeg is able to produce more accurate segmentations than an automatic model trained on these evaluation tasks. And so I think this kind of shows the value of why these interactive systems are important to enable users to segment with a high degree of accuracy. Our main evaluation of MultiverSeg, though, was simulating the process of sequentially segmenting unseen data sets. So this is similar, this plot it's similar to a results plot I showed at the very beginning, where the y-axis is the number of clicks per image to get to 90 dice. So lower is better. The blue line is ScribblePrompt. You have to do the same amount of interaction for every image in the data set. Green is where we combine ScribblePrompt and MultiverSeg. Number of interactions is declining, but more slowly. And with MultiverSeg, there's a more rapid decline in the number of interactions you have to do to achieve this degree of accuracy. So these results are averaged over many tasks, so there is a lot of variability between tasks. For some tasks, you may only need 2 images before you go to 0 interactions, whereas for others that are more challenging, it may take many more. It seems like I lost my animation there. It's okay. So I think another interesting question is how does this MultiverSeg approach compare to that standard approach I introduced at the beginning of few-shot fine-tuning of your model? So we explored this with ScribblePrompt, where we took ScribblePrompt and we simulated the process of segmenting 5 images, and then we fine-tuned ScribblePrompt on those 5 images and continued segmenting the rest of the data set. Generally, this improved ScribblePrompt's performance, so you had to do fewer interactions in those subsequent images. I think another overall takeaway from this plot is that there's a lot of variability in the number of interactions you have to do to segment different data sets, depending on the difficulty of the task. Although fine-tuned ScribblePrompt was better than without fine-tuning, it requires a lot of time training models. Each of those models that we fine-tuned took 20 minutes on an A100. In comparison, MultiverSeg in orange here didn't require any training at inference time. So on the order of milliseconds to do the forward prediction, and in the majority of cases requires fewer interactions to segment the same data sets. So in conclusion, with both of these systems, we made a lot of careful design decisions focused on creating a very user-friendly and practical system for segmentation of new data sets. To build up MultiverSeg, I talked about work from 2 papers, ScribblePrompt, a model that enables segmentation of individual images, and then MultiverSeg, a complete system for segmenting new data sets. I'd like to acknowledge my co-authors on all of these papers, as well as our funding and compute sources. That's the end of my talk. If you're interested in learning more about these papers, both of the projects have websites. It's the name of the model.csale.mit.edu, where there's code and demo and model weights that you can explore. Thank you for listening, and I'm happy to take any questions.
Thank you so much, Hallee, for presenting such an amazing idea. I think anyone from our audience, if you have any questions, please let us know, or I can start. I do have a couple of questions. So like, I like how you have added like the in-context images for the segmentation task. Were you like able to compare it with like Dino V3 or like MedSam2 or like Auto Segmenter, like to have like compare those results with that? Like, yeah, that would be interesting, like to compare with those.
I guess for something like Dino, I think you'd still have to train adapters to fine-tuning the models, and I guess that would still be kind of similar approach, like alternative to automatic segmentation. I think one thing we found with some models, like for example, like MedSam, where you can only prompt with a bounding box, it just wasn't possible to reach 90 dice in like the majority of cases. So I guess our main kind of comparison was to NNUnet, because like that is kind of the state of the art in many cases for automatic medical image segmentation. I guess I have not tried. We evaluated a lot of like fine-tuned versions of SAM1 for medical images. I haven't extensively evaluated the cases where people have fine-tuned SAM2. I'll also say a limitation, a lot of this work is focused on 2D medical images, and so a lot of those papers on SAM2, they're focused on adapting for 3D medical images, and so if they didn't also try to keep 2D capabilities or training images in their training data, I wouldn't expect them to perform well on 2D data.
Yeah, also like it would be interesting if you could add like text for supervision, right? So for example, you have an X-ray, you have a radiology report with that, right? And if you're feeding images along with the text of that reports, would it occur in a better supervision or something like that?
Yeah, I think text prompted segmentation, I guess maybe it's not exactly what you're talking about, but I guess text prompted segmentation, I feel like, yeah, is an area that a lot of people are interested in. I think there's a lot of challenges with doing stuff with text and images in medical imaging due to lack of text data. And I think, yeah, there's a lot of technical challenges in how to augment your text data so you don't just overfit. I feel like a lot of models, they tend to just memorize keywords. And so I'm not sure it's really helping you to memorize, like maybe something like liver. We have tons of images with the liver label. It's probably the most common label in our collection. Like just memorizing this association between the text liver label and the segmentation. I'm not sure it really helps the models generalize. And so I think sometimes training without text data makes it easier for the models to like, you can learn to segment things that you can't describe well in text or are not like objects, basically.
Yeah, even I think like for like if we kind of transition or extend this work to like 3D, right? So for example, it could be a really good application like low-dose CT scans, right? Where you don't have a clear CT, but you still need to like somehow like segment it out, right? It would be an interesting application there as well.
Mm-hmm.
Yep. Anybody else? Any other questions? Yeah, sure, Dana, go ahead.
Can you hear me?
Yeah, we
Yes,
can.
thank you.
Yeah.
I have a question about the workflow of using MultiverSeg for, as an end user. Let's say I have a segmentation mask. Let's say if I'm dealing with brain images, something that I got from FreeSurfer, right? And let's say I want to extend that and divide an ROI into 2, right? But maybe I want to do this for 3, 4 images and not for my entire data set. Is there a way that I could adapt MultiverSeg to do this? Let's say if I have a multi-class segmentation that I already, existing from FreeSurfer or from some older data set, and I just want to kind of indirectly fine-tune this, the FreeSurfer is not going to give me more ROIs, and a new model would still require me to annotate a lot of data manually. Yeah, what are your thoughts on these sorts of problems?
Yeah, I think the workflow would still be kind of the same as what I was talking about, where see, if you don't have any data previously segmented, I guess like maybe what you're kind of asking about, like, oh, could you use these examples of like the larger segmentation regions in the context set? But I think that's gonna.
Yeah, and now let's say that I've segmented all of gray matter, right? And that MultiverSeg, after a couple of examples, can segment gray matter. And then the next step is actually want to segment left hemisphere and right hemisphere. I already have the gray matter segmentation. I want to kind of update that.
Yeah, further subdivide it. Yeah, I guess this current system, wouldn't really help you with that particular case. Although you might be able to, if you have segmentation of the whole gray matter area, you could use that to like crop the images, and that may make your like the performance of the models better by just like you're already limiting the region to predict on. But I guess in this current pipeline, I don't think it would be helpful to provide a context set of a different segmentation task that conflicts with like, what you're currently trying to segment.
Would you then like if I don't know if I understand this correctly, but if I were to download your demo and get the weights, I could use this for some example, and then those weights would not be updated. Where is that state, that information that improves as I segment more and more images? Where is that? And do I just fork it for every application that I have? I get a new set of weights. Or
So the weights are not changing at all. It's just through this context set it's an input to the model, like our prompt to the model. So it's kind of like this whole in context terminology. I think it comes from like in context prompting of LLMs, like where you provide a text example of something and then ask it to repeat that on some new thing. And so these models are kind of behaving in a similar way, where we're not changing the weights of the model, we're just providing different inputs. And I guess actually another thing I didn't mention earlier, this architecture is flexible to different context set sizes, because like we're using the same conv on different inputs in the context set. The architecture can take a variable size context set, so the weights are not changing, just the inputs.
But then if you switch from one image to the other, how do you carry over the context that you've learned from your previous example?
You would just add it to the list of inputs going into the model.
Okay, so literally like an LLM, you're kind of just appending. Okay. Cool.
Yeah. You would you're segmenting an image, and when you're done segmenting it, maybe you download it and add it to some folder that's where the inputs to the model are being loaded. We have there's a plugin in 3D Slicer right now that was developed by Kitware for MultiverSeg, where it basically has this kind of UI that right now it's just 2D. So you're segmenting slices, and then you say, I'm done with this slice. You can add it to the context and keep working on more slices.
Interesting.
Thank you, Daniel. Thank you, Hallee. Any other questions?
Maybe one more question.
Sure.
For tasks where, let's say, the image doesn't have too much contrast, right? Let's say you're not looking at gray matter, but you're looking at the visual system and you want to segment V1, V2, V3, and those boundaries are not super clear. Maybe you have 3 4 different data sets, one with a task MRI where you kind of have one region. Is there a way to combine all of that information? And what would you have recommendations of a workflow? Where would you start scribbling, like as a user, to get maybe there's some learning too as a user that I can minimize the clicks and scribbles by knowing how the algorithm performs best?
Yeah, I guess was the first part that you were mentioning that this data might be multimodal?
Yeah, let's say that I have an image like you're showing here, right? But I want to segment in the visual cortex V1 and V2, where there's no clear boundary in this image. But I have a separate image that maybe I can look at, on the side of the screen, or I don't know if I could load it in somehow as a context. But I want to kind of scribble there. And I was wondering from these kinds of tasks where I could see the interaction being extremely valuable, right? Because it may change from data set to data set. There's no baseline network that would ever predict that sufficiently accurately. What would be, have you guys thought of these problems of, in any way, like combining this multimodal data, or
I think,
just for scribbling?
Oh yeah, I mean, I definitely think that's like one future direction is, both of these models it's a single channel input, but you could easily extend that to take multiple channels. I think the interesting technical thing would be like, can we make a model that flexible to different numbers of channels? Because maybe some data sets people only have one modality, others like neuroimaging, they often have multiple. I guess right now we've only been evaluating on individual modalities. And I think that's ScribblePrompt. One of the things about it, I think that makes it useful is that it's very responsive to user feedback because of this training on synthetic labels. These synthetic labels, they're kind of noisy, but they really force them all to not memorize what to segment, and it has to try to segment based on the user interaction. So I think that sometimes like ScribblePrompt doesn't do as well as like MedSam or some of the fine-tuned SAMs at doing the thing where it's like you click on the lung and it does the whole lung. But this leads to more flexibility, that it's more designed for like iterative refinement, which I think makes it more successful in diverse image modalities. But I think we're still kind of in the process of trying to deploy these models. Like ScribblePrompt is in the dev version of Freeview, if you use that. And continue to try to refine them based on user feedback.
Oh, thank you so much.
Thank you.
Any other questions we have here? All right. If not, let's wrap it up. Thank you so much, Hallee, for taking out time and giving this wonderful talk. For people who want to reach out to Hallee, Hallee, do you have any contact information that they can reach out to?
I guess you can always send, let's see, I'm trying to get back to the end slide. Like we have, there's project pages for both of the projects with links to GitHub. You can always open an issue on GitHub, and you can also email me directly. My email is just my first name @mit.edu.
All right. Thank you so much. All right, everybody. Thank you so much. See you next week with another speaker. Thank you.
Okay.
Yeah, bye-bye.
Thank you.